Okay, welcome back. We have a couple more talks this morning. I'm happy to introduce Bingjie Wang, who is joining us from Princeton University, where she's currently a Hubble Fellow. She's going to be speaking about simulation-based inference for galaxy properties, efficiency, coverage, and new physics. Excellent.
Thank you. I hope everyone's ready for another Astro talk. Where we have lots of pretty pictures again. Okay, so let me just situate us by looking back at the history of the universe. So I know in the previous talk, Joe laid out all those complex, unsolved questions in astronomy, but I want to take a step back and say we actually have a remarkably successful understanding of the evolution of the universe from the beginning to the local universe. So what we're seeing here, this is the Big Bang. And here, this is the afterglow of the Big Bang, what we call the cosmic microwave background. It sort of sets the initial seeding conditions for all those large-scale structures that grow and we see today. So now here we have this dark ages. It's just a bubble of neutral hydrogen. Nothing much has going on. At some point, the first stars formed, and we have those first black holes and galaxies. They kind of start to ionize the neutral gas around them. And at some point, the universe becomes fully ionized again. And now with the local universe, we see those beautiful galaxies with diverse morphological structure, like those giant spirals or like those elliptical galaxies. Okay, so what we know remarkably well and by simulations or by theory is how those large-scale structures evolve, because those are mostly related to the dark matter physics. Even though we do not know what they are yet, but they can be simulated pretty simply because they only interact gravitationally. But baryons, all those normal matters, they are much harder to simulate and to understand. So how does the universe evolve from this initial sort of Gaussian random fields to this diverse pathways of galaxies that we see today is still an open question. And it's also a question that I'm deeply interested about. So to understand how the galaxies evolve, one method, maybe the only method, is to take very deep images of the sky. And there is a noble history of doing this in astronomy. And Joe showed earlier the Hubble Deep Field, which undoubtedly just forever changed our perception of how extragalactic astronomy can be done. But now we have witnessing the beginning of a new era, which is just the launch of the James Webb Space Telescope. This is pretty much, I built my career on the Webb telescope. To put into perspective, this is Hubble. This is a primary mirror that's 8 feet. And this is the Webb. It's much larger, so the resolution power is just enormously. And it's very expensive to build, costs $10 billion. Took about 25 years to build. It's, when fully unfolded, it's larger than a tennis court. And now currently it just orbits around Sun, about 1 million miles away from us. Now, what I'm showing you here, this is one of the Webb's first deep images done by the Uncover survey, which I've been deeply involved with. This is a tiny little field. What we look at is a galaxy cluster field. Those bright ones, those are clusters. So they act like magnifying lenses. So we call them gravitational lens. So with this lens, we can peer deep into space with less amount of time. So just way more efficient to look at cluster field. And the source density is very high. It's a tiny field, but it's about 100,000 galaxies in this field. What I've been doing is to turn this beautiful image into the physical parameters, like stellar mass, how massive galaxies are, and how they are formed as those physical parameters, and from which we can truly learn the galaxy formation and evolution. And just to put into more background into what we're doing, when we take images, we take into different wavelength bands. So they are just across the magnetic field wavelengths, and they prop different physics. What I do is to go from those beautiful images to those physical parameters. The distance, or in astronomy, we call redshift, and stellar mass, gas, and dust content. All right, and now I'm just showing what's the state of art in this sort of stellar population modeling. There are several key ingredients. The first is the observation. With observation, this is a galaxy. Now this is the spectrum, but in most of the deep fields, we have just those imaging bands, those little tiny dots. Okay, and then Well, have data within the forward model to understand how the correlations between those input observational data to those output physical parameters. Many human times, including Jones, has been devoted in those forward models, how to digest all those physics and then predict the light from a galaxy. And finally, we have the prior. Because as we know, it's not entirely local dominated, but also not in the prior domination. So this happy marriage here, we have this Bayesian statistics where, and it forced to think a lot about what priors we put in. And yes, this is the equation we all know and loved. And then what we hope to get is the posteriors of physical parameters. Joe have been talking about how we accelerate these forward models, which allowed us to do a lot of rapid and new inference. But I want to take the opportunity to spend a bit of time to see how important the priors are in those data population models. I would say the data are not that informative. I mean, it's not complete. So we need Bayesian inference. And what I've been spending a lot of time is to think about how we encode what we know about galaxies, because there's real observational constraints and real physics in what's the expectation of how the galaxy in the universe look like, how to encode those information into inference process. And then as a result, we can perhaps get more robust inference. So here, this is several priors I put in. What we're looking at, this is as a number. So this is number density as a function of how massive the galaxy is. This is sort of snapshot at universe about 6 gigayears, about 40% of current age. You can imagine we have just as this axis in time, but I'm just showing a slice here. Just to better situate how this is about the mass of the Milky Way. What this prior says is just at the earlier universe, we expect the whole universe to be less involved because Milky Way has a lot of time to evolve into its current stage. So that's how massive it is. But in the earlier universe, we have just more. It's easier to find those less massive galaxies. This is what this prior is. And then there's a number density prior. The x-axis is redshift or distance. And this is the number density. So basically, this is we can observe more galaxies nearby. Very intuitive. And finally, the star formation histories. A lot of effort have been devoted into sort of give this flexible star formation history treatment, but this is going to be another talk. Basically, here just we match the expectations to the real galaxies. Now, how does this perform in real data? We can do a test case. We have the data as those photometric points, those data points, and the inference this shows the model spectrum. What we want to get is just what the properties of these galaxies. Here, this is the early web results. This inference, which imposes uniform prior. Influence very dead galaxies. This is this huge break. It just the star formation has completely shut down. All right, and in the later paper, we refit it with those physically motivated priors. Well, excitingly, we got a very different answer. Well, I change the scales, but it doesn't matter. You see with those emission lines. The emission lines are powered by stars. So this means this galaxy is not dead at all. They still have ongoing star formation history. Ongoing star formation. Now, what's the ground truth? Fortunately, we can get a ground truth for this galaxy because we can take a spectrum of it. So instead of guessing what the underlying physics or the physical process are from those few photometric bands, we can just point the Webb Space Telescope a longer time to get a full spectrum of this. And this is spectrum of this galaxy. And we see those are emission lines. So it's not the star formation, it has not shut down. This is not a dead galaxy. This is just a good example to show how robust the inference can be if we just add in some well-motivated priors of physics into the process. And then we have this whole pipeline, including the neural net emulators, and apply to this first WebD field. And we produce this one most sophisticated value-added catalog. We fed this about 70 objects and with high-dimensional 6-parameter models. I can just do this in a couple of days in a modest clusters we have at Penn State. So this is just an example of the exotic parameter space we're able to prove by just doing this rapid inference in this brand new web field. As I said, we have do a lot of exciting science with those early data. I'll just highlight the work that I led, which is the confirmation of some of the most distant galaxies ever observed. When you see here, this is at redshift 12, at redshift 13. At the time of writing, this is the second most distant, and this is the fourth most distant galaxies ever observed by a human being. The age of the universe at low redshift is about a couple of 100 million years after the Big Bang. It may sound like a long time, but it's only a fraction of the total age of the universe. So we're really looking at the infant stage of the universe. All right, so this is web in a very deep field, but we also are fortunate to have a revolution in another frontier on the data side, which is the first light of the Vera Rubin Observatory. This is a very different telescope. Web, the point is very small, so we look at a very small field of the sky. But Rubin, this is a survey parameter. It's a 8.4 meter primary mirror. This is the largest digital camera ever built. It's going to cover the entire sky in every few nights, so create the largest astronomical movie of all time. This is just here, and this is the Milky Way, I think. I don't do local galaxies, but okay. What I'm going to show is just a small fraction of the total survey volume. This is a movie of the first images from Rubin. Okay. Right, so it just sort of, you can imagine, start to zoom out and look at those very different kinds of galaxies. So even though this is a much larger data volume than Webb, it's only a small fraction of the total expected data from Rubin. And the final data product is going to be composed of about 5 billion galaxies. Under the standard inference method, it's going to take us billions of CPU hours. This is prohibitively expensive. Even with acceleration from a neural net emulator, it's not fast enough to digest this kind of volume of data. So that's now it's not obvious how to accelerate the model generation part further. We have those neural emulators, those gradient-based samplers. The model generation will probably hit the limit. About this is as fast as I can. So we need to look elsewhere to deal with this data volumes. That's where simulation-based inference can be very helpful. So I'm just going to take a step back to say what we're trying to do here. In astronomy, basically we have those few metric bands, and we want to get the posteriors of the physical parameters. This is all we care. Currently, those state-of-the-art samplers, we usually use MCMC and that's sampling. Some of the implementations are like some of the highest cited papers in astronomy. But to speed up inference, I guess to this crowd, I don't need to expand further. We can replace this whole pipeline with normalizing flows. So we can just bypass the likelihood and then get the posteriors super fast. So, okay, I will just spend very few time to briefly go over what we want to do with simulation-based inference in this population inference. So we can sample the physical parameters like stellar mass, formation histories from some priors. And then from the generative models, forward models, we get those data points. So those are simulated data. We train SPI model to predict those physical parameters. And then we pass the measured data to the estimator to attain posteriors. Importantly, SPI, as we know, based on density estimations, is amortized. This means the very computationally expensive step of generating billions of models does not need to be repeated every time we run a fit. This is super desirable for stellar population inference because the model generation is just it's very computationally expensive. Okay, does this work for astronomy data? We run a test. So we sort of train SPI and then see how good we can do compared to the standard art simulation methods. So here I'm just showing the increase in the speed. So this is number of posterior draws versus time. So yeah, as we draw more posterior samples, the time sort of increases, but still it's very fast. It's on the order of seconds. Right, and this is the recovery test. So we tested on test set. This is a true distance or redshift. This is a posterior median. Here showing green, this is a state of art. This those we use as a benchmark from necessary sampling and those old codes. And in orange is from our baseline SPI model. And you see they overlap very well. So we can say SPI performed at least as good as this traditional state-of-art method. And if you look closer, this is the scatter. This is the outlier fraction, and this is the median bias. It looks like the SPI works like better across the full across the board. We take it as highly suggestive that if the data closely following the training set, the SPI can perform exceptionally well. Well, with this increasing speed, we can get such a good answer. Maybe this is too perfect. Well, there's a little footnote to the SPI applications to astronomy, which is SPI, because it bypasses this whole likelihood calculations. It requires the observed data to have identical characteristics to the simulated data. What this means in the astronomy context? Well, let's start from when we create a training set. We have simulated those noises data, photometric data, in a set of predefined filters. So those are the data points. Then this requirement means the input data must be complete. If we train it on a 7-band photometry, it's the baseline SPI. It can only be applied to a 7-band photometry. And second, because we need the actual training set is composed of noise simulated data and the model noise. We sort of condition on the noise. Then this means the noise properties must be stable. Otherwise, we cannot have a noise model to let a training set to propagate the noise into a training set. However, astronomical data often violates those two assumptions. To start, the various sky and telescope conditions can create those very large uncertainties, or we call out of distribution measurement errors. This example here, like those are the normal noise, but in some bands we can have very large error bars. And maybe worse is we are often looking at heterogeneous data coverage because when we combine the survey data, like from different telescopes or different surveys, their coverage in the wavelength states may not be identical. And this creates a problem of we call the missing band. You can imagine, well, instead of a full 7-band or so coverage, we do not have photometric bands. Then the question we were interested in answer is whether SPI is really useful in real applications of astronomical data. So we sort of, this is Josh Spergel's idea, who was here yesterday, but so we want to see if we can expand the usage case of SPI, and we come up with this thing to deal with a variety of messy data. We call it SPI++ because it deals with two problems. So the idea is pretty simple. When we have an out of distribution measurement errors, we can approximate it still as Gaussian sort of distribution. The underlying noise distribution is just a wider Gaussian. And then we draw those samples from these wider Gaussians and then apply it with this normal expected small noise. And then we pass it to the baseline SPI, and we do it many times. So we multicolor over it. And then finally, we just average over the posteriors. This averaged over posterior give us the final posterior estimations. And similarly for the missing bands, well, if one band is missing, we can do a simple like nearest neighbor search. So we look into a training set to find the nearest neighbors and then sort of guess what this missing band is. Gives us distribution. And then we draw multicolor samples, pass it through the baseline SPI, and again, average over all the posteriors, give us the final estimation. This is all completely SPI-based. The multicolor procedure increases runtime a little bit, but still, it's can work in principle. So does this work? We again did it on a test case. This is a test set. I'm just showing a few of those most important physical parameters: distance, mass of galaxy, and its star formation rate. In light blue, those are the posterior samples from the standard method, from nested sampling. I should say the truth is it get the truth right. I just didn't put the truth. And in darker blue, this is where we do these multicolor procedures, pass the new SPI method. And see they overlap, so we can get the answers pretty good. Or we can ask, what if we just naively pass the auto-distribution measurement errors to the baseline SPI? And this will get those orange contours. And the truth is somewhere here. So it can be very wrong and with high confidence sometimes. All right, and then this is for the missing data case. Because we have missing a band in the input data, so it renders it completely inaccessible to the baseline SPI. Again, the grayish contours are from the standard method. And then over on the purplish color is from the SPI method. Again, they overlap on top of each other, so meaning we can get the truth and the procedure pretty well, at least on par with the standard methods. But with a huge increase in the computation efficiency. Okay. And I would say, well, those are just on test case. It's essentially a bug test. How does it perform on real data? Just as I was doing this work, we have a first batch of James Webb data. So we just applied the SPI model on those brand new Webb data. Here I'm just showing the distributions of each of those are a galaxy. So this is the brightness. Here just a fainter. Positive means it's a fainter galaxy. And then this is the uncertainty associated with each of the points. So you see, those are different layers. So the noise is not that simple to model if we want to just derive one just to totally encapsulate the complexity of observed data. There's physical reasons for those different structures because they have different depths, each of image that creates those stripes on this plot. Well, for our testing purpose, we did the noise model as simple as we can think of, which is a noise estimated from some mock catalog. It does. We didn't even bother to look at real data and estimate noise model, but just use the mock catalog and then pass it through the SPI. This is the result. A fraction of the samples has spectroscopic redshift, which we take as the ground truth. This is the photometric redshift, which is the inferred redshift from those methods. This is the one-to-one correspondence line. In black points, this is state-of-art standard method to get those redshifts. And in red is the redshift inferred from our SPI pipeline. If we look at the summary statistics, they did perform equally well. I should say the black points really represent a state of art in this redshift inference. And now we can at least say we have a pipeline that runs way faster, but can be as good as the standard methods. Furthermore, what caught our eye is those error bars. So if you look at those black points, they get the wrong answer, but with high confidence. This causes real problems. We want the posteriors to be well calibrated. But in red, from the SPI method, they can get the answer wrong, but with huge uncertainties. So that was way better. It means we can propagate the uncertainty into the rest of the physical parameters. I should say, if we get redshift wrong, we get everything wrong, like stellar mass formation histories. So a real well-calibrated posterior uncertainty is really important to do any of those formation models. All right, so this sort of is a promising way to move forward to scale up our inference pipeline. And more recently, there are a lot of developments trying to apply this on other sorts of large data. I'm just showing one example that I've been involved with, which is this real-time characterization of transient hosts. By transient, just like for a supernova, it can explode on the sky. And when we have a Rubin observatory, we like sort of map out the sky in a few nights. So we can see a lot of supernova, all those stars exploding on the sky. But there are so many of them. We have a limited resource to decide which one to follow up. This means we need a really rapid inference to understand like how special this star is, and then is it worth our time to do more follow-up works. For standard, we just can't wait for like 15 hours using standard methods. It does not work. So the idea of this is we implement SBI into this whole pipeline and then try to do real-time characterizations of those supernova host galaxies. This is a fully public web portal. You can just go ahead and then it will give you a list. So the International Astronomical Union would have a real-time monitor of all those transients on sky, and then we just take them in, find their positions on sky, extract the light in different filter bands, and run those population models. And then there's a more recent work. Okay, this is madness, but I include this figure because it looks cool, but it doesn't matter what those are. They are just sort of the next step in preparation for the Rubin era, which we ingest all those transient and do rapid inference. And then it really opens door for those population level statistics. So far, this field has been limited to a finite sample size that prohibits to do any sort of large-scale population studies for how well does there any difference in the galaxy that hosts different type of supernovas. So this really opens door for that. And with Rubin coming online, we can do some new exciting science with this. Okay, and then. So in the previous talk, Joe presented all those complex problems, and I want to end with a positive message. This is not usually how our conversation goes, but here I want to send a more positive message. With all those developments in the inference pipelines, can we really qualitatively improve our understanding of galaxy formation? And I think the answer is yes. So Joe showed earlier that with a high signal to noise spectrum or data from web, like it's probably the best as we can get, we cannot recover the complex behaviors in the star formation histories just by fitting individual galaxies. We need to look for populations. So Joe showed you the promising aspects of doing this on a population level. And the hope is once we empirically measure the population level distributions of birthday star formation histories, we can learn the true birthing priors and then put it back into our inference. And this just shows how it works as a proof of concept. So what changes between this sample and the really bad fits we see in the earlier talk is just now I inputted correct prior that knows how birthday is or how the duty cycles of those formation history is. And then we can get the answer really well. The truth is in those dotted lines, and the inferred star formation history is in purple. So there's, real hope to understand. And then, so that can be used to solve outshiny. And the other big problem in galaxy formation study is selection functions. So when we want to do those, like, say, how galaxies evolve across cosmic time, if we do not have a complete samples, it's really hard to say, do we understand its population? Once we understand burstiness, because they can fluctuate in out of your observing limit. So once we understand burstiness, maybe we'll have a complete sample of galaxies in the first black holes. Finally, and I am the PI of the Cycle 4 web programs. Right. Well, if you look at title, it has nothing to do with selection functions, but we are coordinating with a few other smaller programs to have well-selected, uniformly selected spectroscopic sample, which we can back out the selection function. You cannot get the tech super excited about uniform selection function, but you can get them really excited of those model-breaking objects. So the hope is by coordinating a few small programs, we can finally arrive at a uniformly selected sample, and we can do many population level statistics. Okay, and then I will end what I envisioned to be the future of galaxy formation studies. There's a complete new census of galaxy formation. Again, right, all models are wrong, but some useful. When we fit the data, it's not that informative. A lot of model assumptions can fit the data equally well. And we talk about, say, the bursts in star formation history. This is the truth versus the backed out. This is a fiducial, so we assume no bursts, and this is the cell mass if we assume burst in star formation. So it increases the scatter, right? This is log scale, so the scatter is pretty large. And we also talk about the nebula abundance. If we just change the abundance, it creates a symmetric shift in the stellar mass. But those are solvable, right? So you can imagine once we understand how bursts in this are, we put it into inference, and then we can get better understand our stellar mass, and then nebula abundance. We have those emulators to do this better. And finally, we haven't touched is initial mass function. This is what I hope we will be solving in the next few years. This sets the conditions, initial conditions of the distribution of stars. If we change it, it changes everything. So this is sort of a scary topic we just never dare to touch. But with those rapid development from the inference and those physical studies, there's maybe hope to wrap this all together into one complete inference and can finally arrive at unbiased census galaxy formation. And with that note, I will stop here.